Part 3, how to rotate any graph by any angle. Alright, I don't want to run out of time again, I want to finish up this time. So let's just jump into it. 3D rotations, here we go. I'm going to show you two ways to do a rotation in 3D. There's the easy way, and there's the beast way. We are going to do both. But first, we'll begin with the easy way, using the power of linear algebra. Linear algebra, in other words, linear transformations and matrices. Yay! Here's the thing. Either you've studied linear algebra before, and you already know exactly what a matrix is, and what a linear transformation is, and me explaining it to you is going to be as interesting as an engineering lecture. Or you haven't learnt linear algebra yet, in which case it will take me like 15 minutes to explain. Unacceptable. Nope, we have no time for that. So if you want to learn about this stuff properly, the proper way, there's like a billion other videos out there. 3 Blue 1 Brown has probably done a whole series on linear algebra. Probably with his absolute perfect animations, specially made in his custom-built Python library. First of all, what is a linear transformation? Why don't I just show you? A linear transformation allows us to do things like stretch out the x-axis and the y-axis. But more than that, we can also change their directions. We can make the x-axis go up at an angle. Yeah, and we can also move the y-axis around too. We can flip the plane all the way around if we want. Rotate it, skew it, stretch it, squish it, etc. All of these are linear transformations of the plane. Okay, now technically there's no 3D in this at all. Technically there's no 3D, but it kind of looks like there is. It kind of looks like we're angling up the normal 2D plane and rotating it around in the third dimension. Yeah. Alright, anyway, let's go back to our good old sine wave, y equals sine x. Of course, we know how to rotate this around the origin. Change the x's, change the y's, yeah. But now consider this. What would happen if we did a linear transformation on the plane while the sine wave is still spinning? There you go, a 3D rotation, naturally. Okay, that's great. How does this work mathematically exactly? Well, if you've learnt linear algebra before, you'll know the way we encode a linear transformation mathematically is using a matrix. Specifically, the matrix ABCD. And the official rule goes like this. The matrix ABCD times the point xy equals the new point ax plus cy, bx plus dy. But the truth is, this rule, it doesn't really matter. And the matrix itself doesn't really matter either. All that matters is we start at the point xy, and the linear transformation tells us to go to the new point ax plus cy, bx plus dy. Okay? Or to put it another way, the x-coordinate turns into ax plus cy, and the y-coordinate turns into bx plus dy. That's what the linear transformation does. So, let's come back to our sine wave. And we just do the same thing. Change the x's into ax plus cy, and change the y's into bx plus dy. Alright, now for some examples. First of all, note that if we let a equal 1, b and c equal 0, and d equal 1, then we get back our normal flat spinning sine wave. Alright, so what about if we increased d to 3? Looks like it's facing up more vertically. Alright, what if we increase a instead? Ah yeah, now it faces out horizontally. Okay, and if we start changing b and c, that's how we get it to face a diagonal direction. In theory, you can do any direction, but the tricky part is figuring out how to choose A, B, C, and D. Meh, whatever. If you know linear algebra, you can do it by calculating the inverse matrix and mapping the standard basis vectors, but that's annoying. And besides, if you stare real closely, you might notice that something ain't right. This is actually not a true, proper 3D rotation. In proper 3D, things appear bigger when they are closer to you, and they appear smaller when further away. But sadly, linear transformations don't do that. Linear transformations keep everything the same size. So, it's kind of a cheat. And you know what that means. Finally, the moment you've been waiting for. But in order to do a perspective projection, we're going to have to switch to 3D geometry. Yeah, we're going to need a z-axis.
But Red, you said we wouldn't need a z-axis.
Yes, I did. I lied. Nah, here's the thing. There's 2 steps. Step 1, we convert our graph into 3D and rotate it properly in 3D space. Okay? That's what we need the z-axis for. And then, step 2, we project the 3D space onto our 2D plane. That's the projection, and that's when we'll get rid of the z-axis. Yes, we'll get rid of it in the end. Don't worry, but we need it to begin with. Trust me. Actually, no, don't trust me. You know what? Screw it. Let's just do the projection part first. Why not? So we're in 3D space now. That means our points are no longer just 2 coordinates, they have 3 coordinates, x, y, z. But we don't want them to have a z coordinate, so we have to find a way to send any 3D point to the usual xy plane. Okay, so one way we could do this is by sending xyz to the point xy0. In other words, basically we just drop the z coordinate. We could do that, and in fact, actually we already did that, back when we did the linear transformation. That's what the linear transformation was doing. But it's not the only way to do it. There is a better way. Imagine you are standing on the z-axis. You're on the z-axis and staring directly at the xy plane. Okay, what we can do is draw a straight line from your eyes to the point P. This line goes through P, and somewhere along it hits the xy plane at some new point. Okay, now we're going to define this new point to be our projection of P. Okay, so you can imagine this line is like a ray of light that's coming from the point P, and it's hitting your eyes. That's how you see things. Literally, that's how you see. But if you were to draw what you see in real life onto a 2D screen, like the xy plane, then of course you would draw P at its projection. And that's the idea. Okay, so how do we do this mathematically? First, we need to decide where we are exactly on the z-axis. I'm going to choose the point 0, 0, 30. But you could choose any other point you want. It doesn't matter. Although, I do recommend not choosing one that's too close to the origin, because then you might not be able to see much. Anyway, I'm not going to go through the actual maths, but basically we just connect 0, 0, 30 to the point P to get the line that goes through both of them, and then we can find the point on that line where the z-coordinate equals 0. That gives us the projection point, and it turns out to be 30 divided by 30 minus z times xy0. 30 divided by 30 minus z times xy0. Projection complete. Now all that's left to do is drop the 0. Yep, we just get rid of it. 30 over 30 minus z times xy. And we are back in 2 dimensions again. Back in 2D. Nice, that's it. To project our 3D point xyz onto the xy plane, we just convert it to 30 over 30 minus z times xy. Big box. Remember this. Do not forget. This is very important, and we will need this later. Because that was step 2. Now we got to go back and do step 1, the actual rotation. First things first, we got to choose our graph that we want to rotate. And that's actually not so easy to do in 3D. For example, in 2 dimensions, we can just write y equals sine x, and that gives us a nice sine wave. But in 3D, if you write y equals sine x, you don't get a line anymore, you get a whole plane. No good, we don't want any planes, only lines. Now we could write something like y equals sine x equals z, and that does work for simple graphs. But if I write something more complicated, like y squared equals sine of xz equals x plus z, that's impossible. I have no idea what this even looks like. And computers don't either. Probably no one knows. So long story short, for 3D, we're just going to abandon Cartesian equations. No more Cartesian, only parametric. And parametric is much better. X equals f of t, y equals g of t, and z equals h of t. We're pretty much guaranteed to get a line with this. For example, we can try x equals t, y equals sine t, and z equals t. This is the graph of a diagonal sine wave. If we change z equals t to z equals 0, then we get a flat sine wave. What if we swap x and y around? Now it becomes a vertical sine wave. My favorite one is a spring. X equals cos t, y equals t, and z equals sine t. And there's more you can try, obviously, but sometimes they can get a bit hard to wrap your head around. That's why I like the spring. It's very intuitive, but not trivial. But it doesn't matter anyway, because in general, every parametric graph has the form x equals f of t, y equals g of t, and z equals h of t. Yep, we're just going to go straight for the general case, like men. We can try some examples at the end. This is our graph. Alright, now we want to rotate it. How do we do that? With this! Ta-da! I got this off Wikipedia. It's called Rodriguez's rotation formula, named after the legendary Olinde Rodriguez. Never heard of him. Anyway, this is the equation we're going to use. Except there's one little problem. Okay, a few problems actually. For starters, this formula is designed to work for vectors. Basically, you give it a vector v, and Rodriguez's formula spits out v theta, which is your vector v rotated around by theta. So we're going to have to find a way to convert these vectors into 3D parametric graphs somehow. Okay, that's not too hard. But more importantly, what is k? K is another vector which describes the axis of rotation. So okay, yeah, you've got your vector v, and you want to rotate v, but you gotta tell me what axis you want to rotate it around. Do you want to rotate it around the x-axis, or rotate it around the y-axis, or the z-axis, or a diagonal axis? Okay, we need to decide that. That's what k is for. For example, if you want to rotate around the x-axis, then you would choose k to be the vector 1, 0, 0. Or to rotate around the y-axis, let k equal 0, 1, 0. For the z-axis, k equals 0, 0, 1. And you get the point. Whatever axis you want, just choose the vector that goes in that direction. That's what k is. There is one teeny tiny technicality. We can't just choose any vector for k. It has to be a unit vector. Alright, k has to have a length of 1. But okay, that's no problem. We can just choose any vector and then normalize it. Fine, no worries. Anyway, now it's time to convert Rodriguez's formula into something we can use. So, first we let k be the vector a, b, c, where a, b, and c are constants. Next up is the vector v. Now v is the thing we're actually rotating. So naturally, let's call it xyz. V becomes xyz. However, don't forget about our graph. x equals f of t, y equals g of t, and z equals h of t. This is our graph, and the graph is what we really want to rotate. So actually, x, y, z is really f of t, g of t, h of t. Ah, yeah, it's all coming together now. We've got all the pieces. We just need to assemble them. Righto. V is f of t, g of t, h of t, of course. Next, k times v. Now be careful, this is not a normal multiplication. This is a cross product. Cross product of k times v. That is, by definition, b h of t minus c g of t, c f of t minus a h of t, a g of t minus b f of t. Okay then, I guess. Moving on, k is ABC, of course. Then k times v again. Except this time, it's a dot product. Dot product of k times v, which is a f of t plus b g of t plus c h of t. Okay, wow. I am not reading out all of that. And it doesn't look like it simplifies anywhere either. What a monster. Anyway, good news and bad news. The good news is, we've done our first step. We've done the rotation. The bad news is, we're only halfway. Now we gotta project our 3D graph onto 2D. Oh my god. It's okay. We've got the equation. We have the equation right here. All we need to do is plug in this enormous expression into our equation. The final step, the last piece of the puzzle. Ta-da! We did it! But at what cost? Yeah, so it's sort of ridiculous. What'd you expect? It's a 3D rotation projected onto 2D. Alright, we can make it a little more readable like this. X equals 30 alpha of t over 30 minus gamma of t, and y equals 30 beta of t over 30 minus gamma of t. And alpha and beta and gamma are defined as these stupid functions. Better? Fine, you're welcome. Anyway, it's springtime. Let f of x equal cos t, let g of t equal sine t, and let h of t equal t. I have summoned the spring. Now let's see if we can rotate it around the x-axis. Let a equal 1, b equals 0, c equals 0, then crunch through all the numbers, and... oh, what do you know? It actually worked. Can we change the rotation axis? Let's see. Let's try b equals 2. Don't forget to normalize. And... nice. It doesn't have to be a 3D graph though. Just set h of t equal to 0, and we can get back our original 2D graphs from before. For example, here is our good old sine wave, spinning around the y-axis. Can we make a windmill again? Yes, we can. Oh. What is this? Abomination. It looks horrible. Oh yeah, because we're looking at it from the side. Alright, let's just tilt it forward a little bit. Yeah. Wait a minute. Oh no. Now the sine waves are all wrong. They're not flat. They should be flat, like this. How do we fix this? It's actually not totally trivial, but what we can do is use our rotation formula twice. So we begin with our regular sine wave. Nothing special yet, but before we make a windmill, first we use our formula to rotate the sine wave around the x-axis. Yes, that's right, not the y-axis, the x-axis. So now it's facing down, slightly diagonally. And now we use our rotation formula again to spin it around on an angle like before. And then finally, we can add in the other sine waves to make a proper windmill. Anyway, this is the end now. I am done. I am so burnt out. But I did have some more things I wanted to try though. Like I was thinking about a 3D spiral vortex. Not sure what that even means, to be honest. But I don't know, maybe it could be something. Or how about a 4D projection? Yeah, a 4-dimensional hypergraph. Now that would be cool. And it's definitely doable, I'm pretty sure. But how? That I do not know. I know nothing about 4 dimensions. What does a 4D spring even look like? Imagine if I could just type in some numbers and Desmos would show me. One day. Maybe one day.